So what I'd like to talk about now is just a recap on controlling mistakes in our setup. So the first thing that we saw in this space is this idea about how we think about our null hypothesis. So our null hypothesis could be either true or it could be false, and we have two decisions we can make. We can either decide to reject the null or not reject the null, do not reject the null or reject the null. So when the null hypothesis is true, it means that there is no difference. And we don't want to be rejecting the null hypothesis when it's true. If we do that, we commit a type 1 error. When the null hypothesis is false, it means that there is a difference. And that means that we want to be rejecting the null in that case. So when the null is false, we want it to reject, and that is 1 minus beta. So we talk about 1 minus beta, and beta being when the null hypothesis is false, so it's not true, and we do not reject. And so if we're in that square, we call that a type 2 error. So that's the decision grid that we've got. You can just think about that for a moment. Hopefully you've seen this enough for it to sort of stick in your mind. So for type 1 errors, the null is true and we reject it. So there's no difference in the means, and we conclude that there is, right? And probability of making a type 1 error controlled by alpha. And we have set this for the context of that we look at 0.05. Now other disciplines can have quite different levels for alpha. Okay, that's okay because it's a trade-off between different things, and different disciplines and different contexts require us to weight those trade-offs differently. For type 2 errors, the null is false and we fail to reject it. So there really is something going on and we fail to identify it. Probability of making a type 1 error depends on alpha, sample size, data variability, and the size of the difference you're trying to detect. And really it's often that sample size is one that in practice is binding on people. So we've had a bit of a look at these things. So we see that when we change alpha, when we change alpha, it increases the chance of drawing a sample from variety B, which is has a different mean that falls in the do not reject zone of variety A. So if we go from an alpha of 0.01 to an alpha of 0.05, we would reduce the chance of drawing that sample from B that falls in the do not reject zone of A. So we'd be controlling our type 2 error rate. Sample size, you can see that sample size, where does that come out? It comes in via the use of the standard error of the mean, which is the sample standard deviation divided by the square root of the sample size. So if we get a tighter distribution, we get more power, more ability to detect differences, which is really what we're trying to do. And then for a given sample size, if we can control the variability, so that is the random sources of variation, which we do via things like growing our samples in greenhouses or growth chambers, those kinds of activities, that also increases our ability to detect a difference if one is there. So we really like to detect differences if they're there. We really don't want to conclude that there's a difference if there's not really one there. So the other thing that we sort of looked at in this space was the link between sample size and confidence intervals. So we saw that small sample sizes resulted in large confidence intervals, and we referred to the confidence interval as the range of plausible values for the population mean. So if we have a large confidence interval, it's unlikely that we're going to detect differences because the range of values that we do not reject is quite large. Now, some things to know. So confidence intervals, how to think of them. They're a good representation of where we think the population parameter exists. We calculate them from observed data, but it does not mean that we actually will have the population parameter in our confidence interval. We can't be certain of that. It's just a good representative range for where the population parameter will be. And in terms of, in or out, the population parameter either is in the 95% confidence interval or it is not in the 95% confidence interval. There's not a chance, a probability in that it either is or it isn't. I'll try and illustrate that in a moment. So confidence interval does not mean 95% chance the true parameter value lies in the confidence interval. It does mean that it's a reasonable range for thinking about where the population parameter lies. All right, and this is a very tricky concept to get your head around, but let's have a look if we can make some sense of it with this example. So here we have what we know is the population value. Okay, so and this is when you do simulations, we know what the true population is. So the true population is 17. So each time I get a data, so this is the population, I draw a sample, and for that sample I construct the 95% confidence interval, and that's this guy here. So the population parameter never changes, but then if I draw another sample, my sample mean and my sample 95% confidence interval will also change. So you can see the next sample, this is what I deem as my plausible range for the population value. So in truth, I don't know, like if we're actually conducting our experiment, we don't know what the population value is. I'm telling you in this situation, because with the samples are simulated from a fixed population that I've set, I know what the population is. But we never know that. But by looking at the data this way, it's giving us some insights into how these confidence intervals work. So for what we see is for each data sample that we take, the confidence interval changes. Population parameter is the population parameter. It's always the same. Confidence interval bounces around, but what you see is that generally the population value is in these guys. And because I've set them at 95% confidence interval, by the time we got down here into whatever this is, the 19th simulation, you can see that this confidence interval, actually like the dot is looking there, it just excludes 17. So I drew a sample and my sample does not include the population parameter. For the previous 18 experiments, it did. And for the next however many I do, it's likely to as well. But occasionally I get one 95% confidence interval that doesn't include the proper population parameter. I would say though that if you look at this, you can see that it's not that far away from including the population parameter. So even if we were to take this sample where it happened to be one where we didn't include the population parameter, you can see by saying, well, I think it's probably somewhere between here and here, you're still not likely to be that far off. But generally, your confidence interval, gives you a range of values where it's likely that you're going to capture the true population parameter. So each sample gives you a different confidence interval. So confidence intervals are specific to the sample. The population parameter never changes. Most of the time, the confidence interval will include the population parameter. Occasionally, it won't, so we don't know that. But the population parameter itself either is in the 95% confidence interval or is not. It can't be a probability. It either is in or it isn't. So that's the confidence interval being each representation. So hopefully that's an idea of, you can see that confidence intervals are not a perfect measure. From time to time we'll make mistakes, but in general they provide a good sound idea of where the population parameter lies. So what have been our testing concepts so far? So we've had the t-test, which we've seen comes in 3 flavors, follows the t-distribution, values close to 0 for our test statistic mean that we have little evidence against the null. When we get values far from 0, it's strong evidence against the null. Our 3 flavors of t-test, and for the 2-sample t-test, we saw that we needed a pre-t-test test, which was the variance ratio test. Then we've set up our testing structure. So state the null and the alternate, set the alpha, conduct the relevant test, and apply the p-value decision rule, say something useful about the context. So that's pretty much how we've gone about our business so far, and that's because we've been looking at just 2 groups. So now I want to just extend you a bit, and before I pull your thinking beyond looking at 2 groups, I want to just bring in at least one way of thinking about some probability concepts. So here's the idea. If I roll a dice, what's the probability of obtaining a 6? Well, this is not rocket science. Okay, we can enumerate all the possible outcomes. 6 is one of those outcomes. The probability of a 6 is 0.16 or 0.17 rounded. Okay, so let me just flip that around. Again, might seem a little bit trivial to start with, but let's work with me here. What is the probability of not rolling a 6? Okay, again, I can enumerate all of the outcomes. The possibilities that are not 6 are 1 through 5. So the probability of not rolling a 6 is 5 out of 6. All right. And of course, you can see where there's not much hiding here. The probability of obtaining a 6 can be written as 1 minus the probability of not obtaining a 6. And like many things, there's always a reason for this convoluted language. Now, the way that we can then work out things when we have multiple ideas on this is this more specific formula down here. It's 1 minus the probability of not rolling a 6 times the number of rolls of the dice. So because we only had 1 roll of the dice, we had a 1 sitting up here. So it still gives us 0.16. But now let's think about when we have multiple rolls of the dice, all right? So the probability of rolling at least 1 6, that's going to be the thing that we want to do. So let's have a look at this. So with 2 rolls of the dice, it's still possible to enumerate all the possible outcomes from our dice roll. So this is my first roll, my second roll, my first roll, second roll, and so on. So if my first roll is a 1, then in my second roll, I could also have a 1, a 2, a 3, or 4, or 5, or a 6. All right, so if you go through, if I roll 2 die, what is the chance of rolling at least 1 6? So you can see all of the combinations that include a 6 have been highlighted in red, and we can see that 11 of the possible 36 combinations include the chance of rolling at least 1 6. We could get a 6 on the first roll, we could get a 6 on the second roll, and we work out all the possible combinations of rolling at least 1 6. We have 11 out of 16. All right, so again, let me flip the question around. What if I was to say, what is the chance of not rolling a 6 from 2 fair dice? Again, all the combinations that weren't red before are now red. These are all of the chances that you could not roll a 6. So you can see that there are 25 out of the 36 possible cases where you do not roll a 6. So let's go back to the formula and let's just work through all of these things to see how it makes sense. So chance of not rolling a 6 from an even dice from 2 rolls. First roll, second roll. So not rolling a 6 on the first roll, the chance is 5 in 6. Second roll, 5 in 6. So 5 in 6 squared, 0.69. So from this we can work out the probability of at least 1 6 is 1 minus 0.69. So 0.31, which is what we found from our direct application. So what we've got down here is then the probability, so 1 minus probability of rolling, of not rolling a 6 to the power of the number of rolls. So 1 minus, if you work it all out, you get there to the 0.31. So what we're seeing is that there is a way we can apply a formula from using this strange concept of not rolling a 6 when we're trying to work out the chance of rolling at least 1 6. Okay, so the chance of rolling at least 1 6 from 4 rolls. So by the time we've got to 4, it's starting to become difficult for us to enumerate all the possible outcomes. So then it really does become valuable to fall back to our formula. So here's our formula, and you can see, well, we know this. What's the chance of not rolling a 6? 5 out of 6. 4 times 1 minus 0.83 to the power of 4 gives me 0.52. So the chance of rolling at least 1 6 from a fair dice from 4 rolls is 0.52. So if you have 4 chances to roll a 6 and you need to roll at least 1 6, you've got a slightly better than 50% chance of doing that. So what is the key result from this exercise? We can see that this probability, as we increase the number of rolls, we can see this pattern of slowly increasing in smaller steps the chance of rolling at least 1 6. And what's important for us to know is this general expression that we've got down here. So what have we got? Now we're going to come back to type 1 errors. So type 1 errors. What's a type 1 error? A type 1 error is the chance that the null hypothesis is true and we reject it. So the chance of making a type 1 error is 0.05. The chance of not making a type 1 error is 0.95. So the chance of making at least one type 1 error from 2 related t-tests, we can bring in this formula that we've just seen from probabilities to try and make some sense of what's going on here. So for us, instead of what is the chance of not rolling a 6, it is what is the probability of not making a type 1 error. So if we're going to have 2 related t-tests, the probability of not making a type 1 error across those 2, or at least one type 1 error across those 2 t-tests, is 1 minus 0.95. So that is the probability of not making a type 1 error in any one t-test to the number of t-tests that we're doing, which is 2. So 1 minus 0.9, 0.1. So if we have 2 related t-tests, the probability of making at least one type 1 error across those 2 tests is not actually 0.5, is actually 0.1. So there's been quite a marked increase in the chance of making a type 1 error if we have related t-tests. So the chance of making a type 1 error is this general formula here. 1 minus the probability of not making a type 1 error, which is controlled by alpha, to the power of the number of t-tests that we make. So if we had 3 related t-tests, we can see that if we plug that into the formula, the chance of making at least one type 1 error when we have 3 related t-tests is 0.14. If we had 4 t-tests, then the chance of making at least one type 1 error is 0.19. So you can see the more related t-tests that we do, the greater the chance of making a type 1 error. And that brings in the concept of the family-wise error rate. So when we have our type 1 error rate, it only works for that single t-test. When we have multiple groups with multiple comparisons, we're going to have a problem with our type 1 error rate. If we want to compare a whole bunch of means, this type 1 error rate is going to explode. And you can see that this way that this explodes with this sort of setup here, you can see that if we have 3 groups, we have 3 comparisons. But by the time we have 4 groups, we actually have 6 comparisons. So with 6 comparisons, the type 1 error rate is going to be really increasing. So what do we know? We know that we have a general formula for how the type 1 error rate is going to increase when we do multiple tests. It's usually represented as 1 minus 1 minus alpha to the power of c. Okay, and we can see the scenarios for us. 3 groups, we're going to have a type 1 error of 0.14, but for 4 groups, which is a pretty common scenario that we might be looking at, very common in fact, 0.26. So we're going to have to do something about that. So we have a number of different adjustments that we can use. The most forceful adjustment is the Bonferroni adjustment. It basically corrects, it says, well, if we're doing this many tests, adjust the p-values by the number of tests. So you take the unadjusted p-value and you multiply it by the number of tests. Holm is a refinement of this process. So it tends to be the one that's the default in R. So there are a whole number of these tests. So most of these adjustments are available in the software that we use. One of the most commonly seen adjustments is this Bonferroni adjustment, and that's an option available in R as well. How does it work? It says take the p-value and multiply it by the number of tests. The home adjustment is a refinement of that, which has been shown to be an improvement on, and it's going to move again, isn't it? An improvement on Bonferroni. And the home adjustment for this type 1 error rate is the default that's programmed into R when we use the automated packages. So that's going to be fantastic for us. We've got one of the most effective adjustments for controlling the family-wise type 1 error rate already pre-programmed as a default. We're going to see that we can change that, but that's going to be the one that we'll primarily use. So what has our issue been? Our issue has been that when we conduct multiple, so here, this is our issue. When we have multiple t-tests, the type 1 error rate explodes. So we're really worried about that. We don't like making type 1 errors. What would be a type 1 error? A type 1 error is when we're deciding that there's some difference that's not really there. And if we do multiple t-tests, we're in high risk of doing that. So 4 groups is common for us. So when we have four groups and we compare all the groups, if we make no adjustments, the chance of making one type 1 error, or at least one type 1 error across those 4 t-tests, is actually a quarter. So that's unacceptably high. So we need a mechanism to control that. There's a really simple logical way, which is to adjust the p-values by the number of tests that you're doing. So you inflate the p-values and you can still apply your p-value decision rule. This is really logic, intuitively, easily. Some smart guys have shown that there's a slight tweak to the Bonferroni test that works a little bit better than this straight adjust the p-values by the number of tests you're doing. So that was a bit long, but that's an opportune time for a break.